When a cloud bank swallows the nose of your aircraft, your visual horizon vanishes instantly. Without the ground to guide you, spatial disorientation can set in within seconds. To maintain your course in zero visibility conditions, you need a system that can pinpoint exactly how far away you are from a fixed location. That system is your distance measuring equipment, or DME. In this tutorial, we will walk through the exact steps to operate this system. You'll learn to tune the frequencies, decode the signal pulses, read the cockpit displays, and time your final approach. By translating invisible radio pulses into concrete data, the DME provides a mathematical anchor to the ground, allowing you to verify your exact distance to the station even when the horizon is out of view. Let's start with the hardware. In a standard cockpit layout, primary navigation radios are located in the center stack or integrated into electronic flight displays. The ground stations you will navigate toward often combine civilian and military technology. When a civilian VOR station is co-located with military tactical navigation, it is designated as a VORTAC. If a standard civilian VOR has distance measuring capabilities added, it is labeled a VOR/DME. Activating your onboard equipment is simple because the frequencies are paired. Once you dial in the local VOR frequency, the DME transceiver tunes itself automatically. You verify you have captured the correct station by listening to the audio broadcast. You will hear a standard Morse code sequence identifying the VOR, followed immediately by a distinct, higher-pitched sequence identifying the DME. This diagram shows the data. Whether using a dedicated gauge or a glass cockpit, you receive 3 critical readouts: distance to the station in nautical miles, calculated ground speed in knots, and elapsed time to the station in minutes. By linking the radio frequencies and consolidating these 3 data points on a single screen, the system calculates your position for you. You spend less time doing manual math and more time flying the aircraft. The distance calculation relies on a small blade-type antenna physically mounted to the underside of the fuselage centerline. This diagram shows the process in action. The aircraft transmits a string of integration pulses in the UHF frequency range. The ground unit receives those pulses and instantly returns a signal back to the aircraft. The onboard equipment tracks the exact amount of time it takes for that signal to travel out and back. It then converts that round-trip time into nautical miles. But the signal travels in a diagonal line from the aircraft down to the station. This creates a measurement called the slant distance. Because your aircraft is at altitude, this diagonal measurement is physically longer than the flat distance along the ground. To see how this affects your readouts, look at an aircraft flying directly over the ground station. The horizontal ground distance is 0, but the DME will still display a positive distance reading, representing the vertical altitude down to the antenna. If you rely on the slant distance without factoring in your altitude, you will assume your aircraft is further from the runway horizontally than it actually is. As you descend out of the clouds and align with the runway, you will regularly use instrument landing systems or localizers equipped with DME. During this phase, you monitor the nautical miles counting down to verify your precise location as you cross approach fixes and altitude thresholds. To manage your radios during the descent, you use the hold selector on your DME panel. Engaging this toggle switch locks the DME onto the current frequency. With the distance feed secured, you can tune your primary VOR selector to a different station entirely to track a crossing radial. Separating the DME from the primary VOR gives you a continuous distance readout to the runway, while actively cross-referencing a second point on the map. This keeps your situational awareness high during the most critical segment of the flight. Operating the equipment requires following a strict sequence: tune the paired frequency, verify the audio signal, read the distance while accounting for the slant range, and engage the hold selector for multi-point navigation. By utilizing those invisible UHF pulses, you generate the objective data needed to guide the aircraft toward the runway. If this breakdown improved your cockpit workflow, please like this video and subscribe for more step-by-step flight tech tutorials. Mastering the DME provides the objective distance data required to coordinate your descent and execute a professional landing with consistent accuracy.